not because the wall's gone, that's because our lasers have to be adjusted still to map out the entire surface. So really, we're still working on that. We didn't get quite as far as we wanted to. There's a huge learning curve to use LabVIEW and to do this image processing. But we made it decently far. I'm proud of our progress, and I think we're at a good place. So if we could hand it over to anybody, they would be able to take it and get a lot farther than we will. Okay, I'm going to turn over to Brian, the electrical and mechanical engineer of our team.
All right, thanks, Matt. The past few months around the engineering building, I've been known more as an electrical engineer than an actual mechanical engineer. But I assure you, I will be graduating with a Bachelor's of Science in Mechanical Engineering.
Are you sure about that?
I think so. The control system is basically the entire electrical system of the robot. Everything needs to be controlled easily and be carried in and out of the boiler quickly and set up quickly, and that requires a lot of different little pieces and ways to transport it in so it can all work seamlessly. The control system of the robot it basically consists of speed control of the motor that actually drives the robot. We also have incorporated a solenoid, which Stephen was telling you about. It actuates a spray can, so we can mark the wall. The control system also will communicate and process the sensor camera data and be able to communicate with the pan-tilt zoom camera. And all of the electronics required for these components are all in this yellow utility box up here, which can just be carried into the boiler, plugged a few wires in, and it's ready to go. The umbilical cord, as we like to call it, is the lifeline of the robot. It has all of the data, cables, and everything we need to communicate and control the robot. So inside this yellow cable down here, you can see there's 3 Ethernet cables which all communicate and supply power to all 3 cameras. We have one 12-conductor cable, which is basically our signaling wire, which actuates relays and the lights and the lasers and anything else that we could add onto there that could require power no more than 24 volts. And we have one 2-conductor high voltage line that runs the 90-volt DC motor. We've also incorporated a braided steel cable into the umbilical cord for strain relief of the electrical cables, and also in case of the robot stalling and getting stuck on the wall, we can basically just yank on the umbilical cord and pull the robot down. Now, one of the major components that we wanted for the robot was a user-friendly interface. We wanted a technician to be able to go in there without ever using the robot before, just get a quick 5-minute training, and he'll be ready to operate the robot. So we figured, what's an easier way to control anything than with a simple gaming controller? So I talked to a few computer science guys, and they told me that we can just plug an Xbox controller into a USB port on a computer. So we did that, and we can actually look at the data input through the program called LabVIEW. And what we've done is we have the Xbox controller consists of analog and digital inputs. The joysticks here are analog inputs, and then the buttons, all the buttons are all digital inputs. So the pan-tilt zoom camera runs on one of the joysticks, which is an analog control, and there's also 2 analog controls in the back of the controller which control the zoom of the camera. The other joystick controls the speed and direction of the DC motor. Now we can also, the yellow button there actually actuates the solenoid, and we can program any other buttons to do basically anything we want in the future. Now we're also going to have 2 buttons on the actual robot itself that are going to be considered digital inputs. They're going to be used for the wall removal system. Basically, the person will come up and push the buttons, and it'll actually roll itself off the wall, so they won't have to be standing there with the controller and then someone be there at the robot. We can just have one person operating the robot. Now, how do we control the DC motor? Well, you can see in this picture here that this bottom row of integrated circuit chips and resistors controls the speed control of the robot, And those bigger boxes are the relays, which control various other things. So we have 32 speeds per joystick, 16 speeds in each direction. So the further you push the joystick forward, the faster it's going to go. And also we have the jog function, which I just told you about, which can be controlled from the robot on the buttons, or we can also program that on the controller. This is actually what's inside of the control box. You can see we have the 90-volt power supply, which powers the DC motor. We have a 12 and 24-volt supply, which supplies power to the lights and the solenoid and anything else that could possibly be put on there in the future. We have 3 power injectors, which inject voltage into the Ethernet lines, so we don't have to run separate power lines up to the cameras. We can just get data and power through the same cable. We have a 5-volt DC power supply, which supplies power to the logic circuit. We really wanted a 5-volt supply isolated from all the other power supplies because we didn't want to get any interference or voltage drop in case there was a short circuit somewhere and it pulled down the voltage so the circuits wouldn't work. Inside that black box on the right is actually where the circuit was that I just showed you in the previous slide, and we've incorporated a big red emergency stop button in case anything goes wrong. This is a schematic of how a user input actually gets processed and actually output to the robot. So someone will move a joystick or push a button on the controller. It goes through a USB line to the computer. The computer then can use Microsoft Internet Explorer to communicate with the pan-tilt zoom camera. And also all the other inputs go through data manipulation and matrix math inside of the LabVIEW program. The LabVIEW program then outputs the data to the data acquisition device, which is inside of this black control box. And that outputs logic signals to the circuit board. The circuit board then does its thing, and then it outputs the signals to the relays, which control the duty cycle and the solenoid control, and possibly anything else that the scrubgrass plant would want on there. And now here's John to talk about the wall marking removal system.
Thanks, Brian. So once we realized that we would be able to run up the wall and have video capture capability, we moved on to some of our secondary goals, which included marking the wall. For this, we mainly looked at 2 options, spray can or chalk. We preferred the spray can since that would leave a nice bright, red image on the wall of the boiler. So for this, we ended up finding a fire extinguisher bracket that's normally used for the Baja vehicle, but we were able to modify this so that it would hold the spray can and the solenoid to actuate it. Also, once we had our design set for going up the wall, we realized that there's a lot of pull with those wheels. As Steven said earlier, it's about 450 pounds. And so for removing this from the wall, we needed something that would be able to be operated by a single person and would also be a quick process so we could maximize work time. In some research that we did, we found that 37.8 pounds is a good maximum pulling load per hand for a person. So we have to take the 450 pounds down to a much lower number. And in some testing that we did last semester, we found that the strength of the magnets decreases exponentially as you pull it away from the wall. So with about an inch of distance, we're able to get it to a manageable point where a single person could pull it off the wall. For this, we considered a series of levers, jack screws, and ramps. But ultimately, we chose what is basically a small ramp for each wheel. Basically, what you have here is a wedge that wraps around the wheel, and as the toggle button is pressed, gravity basically allows the wedge to fall down, and the wheel will go over it and get to a point where you could pull it off the wall. This method has both the toggle switch and a brake lever that allows the wedge to roll down on the handles themselves, so the operator is able to keep a firm grip on the robot while removing it from the wall. Unfortunately, the complex design of the wedge was a little bit more than we could complete in time for this presentation, so for the time being, wooden wedges will do. But overall, we succeeded pretty well in meeting our goals that we set in our PDS. Our budget at the end of the first semester was set at $6,000, and thanks especially to some cost savings with the cameras, we were able to just come under that set amount. Our goal was to keep the weight at under 50 pounds, and we did a lot of Swiss cheese type work in this, creating holes and reducing weight where we could, and we're down to an estimated weight of 54 pounds, and there is still some room for putting more holes into the bot. We succeeded pretty well in getting the robot to climb higher than we initially thought, and moving at a much faster speed than we thought as well. And now Sean will share with you some final remarks and conclusions.
All right. I get the fun job of telling you where this thing can be improved. First of all, as we've said, it has a quarter horsepower motor right now. In the future, I know that Jeff's going to take this and throw as much weight on this as he can and run up the wall until it will no longer go. So putting a larger motor on this thing and redesigning the drive system for that is would be a definite must for any team that would want to extend this into a second year. As Matt was talking about with the sensors, they're not quite done. Some things that we do want to do with that, if we can make the program faster, he's made significant steps in that in the last couple of weeks and really improving the speed. And then making the template comparison a more effective one. Also combining that with the controls program so you don't have to be running it through different windows at the same time. And John mentioned our wall removal system as well. Other than that, the things the prototype, it hasn't been done before. We've been having professors in our ear telling us all year that we need to patent this, which to my understanding is the school gets the money. So we haven't really pursued that too far. But it's something that has already been talked about. Jeff's been telling us that other companies have been asking him for this already, and they're really psyched about it. So there's stuff that we see already that we would do, over again. We know we do it better a second time. And I have no doubt that if this project were to take up another year,